Welcome back everyone. So today I have brought another interesting problem from gravitation. It is also from Pathfinder under Check Your Understanding section, question number 6. Right. So we'll explore this question. Generally we don't see the hyperbolic trajectories in gravitation, but we'll explore that through this problem. I hope you'll enjoy it. So first read out the problem once. Two spacecraft of masses M1 and M2 are flying with their engines off in the gravitational field of a star of mass capital M that is much larger than masses of the spacecraft. Speeds of the spacecraft at great distances from the star are equal to v1 and v2 respectively. After passage around the star, when the spacecraft are again at great distances from the star, the spacecraft move with speeds v1 and v2 perpendicular to their initial directions of motion. If during passage around the star the minimum distance of the first spacecraft from the star is r1, what is the minimum distance of the second spacecraft from the star? So you can clearly understand that we will solve for the one case, let's say for v1, and we will check the proportionality and we can manage this for second case as well by scaling the factors. Alright, so let's proceed. First, as I said, we'll observe a hyperbolic trajectory here. Now the question is, when the spacecraft is coming from a large distance, let's say infinity, so the trajectory has two possibilities. Either it is parabola or hyperbola, because these two are not closed curve. Ellipse is a closed one, right? Ellipse and circle, all these conics are closed one. So the trajectory can be parabola or hyperbola. Now there was one line, let me mark that line, that during the passage, 1 minute. Yeah, speeds of the spacecraft at great distances from the star are equal to v1 and v2. After the passage around the star, the spacecraft are again at great distances from the star, and this one is more important. Speeds v1 and v2 perpendicular to their initial directions, right? If it was parabola, let's say this is one parabola. Let's say this is y equal to x square. This is the focus of the parabola. This will be the capital M around which the two spacecrafts are moving. So at large distance, this one will be almost vertical. The tangent to the parabola will be almost vertical, and here also it will be almost vertical. So this will be the initial direction of the velocity v1, and this will be the final direction of the velocity v1. So these two are anti-parallel in direction, right? Not perpendicular to each other. So our given condition is not satisfied by parabolic trajectory. But for hyperbola, it is very much possible that for hyperbola, we know that tangent at infinity is asymptote. So this one is one asymptote and this one is other. So according to the question, these two asymptotes should be inclined at an angle 90 degree to each other, as the initial and final direction of velocities are making 90 degree angle with each other, right? So now I'm clearing all these writings, and we have concluded that the trajectory will be trajectory will be hyperbola. That much we have done. So let's draw a hyperbolic trajectory first. Let's say these are the axes. Just for convenience, I'm drawing the axis, and I'm taking in. I have just drawn one branch of the hyperbola. Or let me show the other one as well. We are not required with this part, but this is the one branch of hyperbola, and let's say, or otherwise, let's remove one part. It will be clumsy a bit. So this is, let's say, one asymptote, and other one is something like this, and these two are inclined at an angle 90 degree with each other. So these angles will be 45 degree. This one also 45, this one also 45, right? So these two angles will be 45 degree, and this one, so this is the trajectory, right? So it is coming with a velocity of v1 at infinite distance, and this is the focus of the hyperbola where the capital M mass is situated, and finally also it will go away with the velocity v1, as we can clearly understood that from energy conservation principle, right? Because at infinite distance, gravitational interaction energy will be 0, all will be kinetic energy, and that will be v1 only. So that will result in a speed of v1 at initial and final condition, right? And now I'm claiming that when the spacecraft is passing through this point, I mean its velocity is something like this, let's say it's v, we'll get the minimum distance. Why? Because at this point, from focus, if we join the line, that will be 90 degrees the tangent, so this is normal. But at any other point, if you draw a tangent and you connect that point with the focus, the angle will not be 90 degree. I mean that line, that point and focus joining line will not be normal at that point, because if you not get the normal, it will not be the least value, I mean the least distance from the focus, right? So at the vertex we will get them, at the vertex of the hyperbola we will get the minimum distance from focus, right, in this trajectory. So let me erase a few things. Yeah, so and at minimum distance we have assumed that the speed will be v, and this one is, let's say I'm denoting minimum distance as r1. Oh sorry, it is given only that it is r1, right? And this, we are dropping a perpendicular from focus to this asymptote. I'm telling you why I'm doing this, because I'm interested in conserving angular momentum about the focus, because the gravitational attraction force will always pass to the focus, so torque about this point is 0 and angular momentum is conserved. So initial angular momentum will be, I'm writing here that L conserved about capital M, will get mv1, and this distance will get, okay, so let me take the equation something like this: x square minus y square equals to a square. Now why I am taking x square minus y square equals to a square? Because it's a rectangular hyperbola. How have we concluded that? Because asymptotes are perpendicular to each other, so it must be a rectangular hyperbola, and I have taken a standard form of rectangular hyperbola. And we all know that eccentricity is √2 for rectangular hyperbola, because if you write that a square equals to 1 plus b square upon a square, here both are same, so it will be 1 upon 1, a square will be 2, and e will be √2, right? So that much you know. So this distance is a according to our assumption, and this distance should be ae, because focus distance of focus from the origin is ae, so this will be √2a, and r1 is coming as √2 minus 1a, right? So this is r1 in this case. So I'm writing mv1, sorry, this distance will be a and a. How? Because look at this right angle triangle, the hypotenuse is √2a, this distance, and this angle is 45 degree, so the other two sides will be a and a. This one is also a and this one is also a. So if we conserve angular momentum at initial condition, when the spacecraft was far away and it was coming towards the planet, so we'll get mv1 into √2 minus 1 times a. Sorry, extremely sorry. This will be a only, this distance I am writing, right? And the second point we are taking when it is at minimum distance from the focus, that is at vertex. So at that point we will write mv into r1, and I am writing r1 as √2 minus 1 into a. So m and a gets cancelled, so I've got v equals to v1 upon √2 minus 1. We'll use this latter. Next we'll use the energy conservation principle between these 2 points only. When it was initially far away from the planet, there was only kinetic energy, that was half mv1 square, no potential energy. Let me write it as 0. And at this point we'll get a potential energy of minus gm capital M small m upon r1 plus half m v square. And now I am using this relation to replace v in terms of v1. We'll write v1 square upon √2 minus 1 square. So rearranging the terms, we'll get a gm capital M small m upon r1 equals to half mv1 square. If we take that common out, we'll get 1 minus root 2 minus 1 whole square minus 1. All these are constant terms, so we are not bothered to calculate anymore. So now I will just check the proportionality, because this G capital M small m will be same for both the cases, and this is also a constant part. This half m is also a constant part. So in the second case, we are just changing this v1 into v2, and we will get instead r1, we'll get in r2 instead of r1, right? So it's clear that v1 square is proportional to 1 upon r1, and that will give us the result very easily. So combining both the cases, we can write v1 square upon v2 square will be r2 upon r1. So r2 will be r1 into v1 upon v2 its whole square, and that's our answer, right? So that's all. It was a nice problem, I guess, as generally you don't deal with hyperbolic trajectories in gravitation, and the geometry of hyperbola is also very beautifully used in this problem. So it's kind of maths and physics mixed one, and I hope you liked it. So thank you, that's all.